All right, so the last part of chapter 5 is about solutions, and solutions show up a lot in biology. So I'm going to talk about how chemists prepare and describe solutions. So first, let's just get some basic terminology out of the way. First of all, a solution is a mixture. Do you think a solution is going to be a homogeneous mixture or a heterogeneous mixture? So our solutions, if you think about like a solution of soapy water, is that going to be homogeneous or heterogeneous?
Heterogeneous.
Let's think about it. Is it mixed evenly, or does stuff settle out on the bottom? I would say homogeneous, right? If we think about a homogeneous solution, it means it's evenly mixed. Ideally, you want your solution evenly mixed. So solutions are usually homogeneous mixtures. Of two or more substances. And typically, what it is you have something called a solvent plus a solute. And we'll describe these. A solvent is the liquid doing the dissolving. Oh, yeah, I forgot my E there. And then the solute, if it's not the liquid doing the dissolving, it's the thing being dissolved. So a good example might be making sugar water at home, right? Your solvent in that case is going to be water. Your solute is going to be sugar. Yep.
Is the solvent always going to be liquid?
Yes. In terms of solutions, you're going to be thinking about them in terms of liquid solutions. Yeah. You can start making mixtures of metals, but those have completely different sets of terminologies. Yep. All right. The next term we have to cover is concentration. And concentration basically describes how much solute is dissolved in a given amount of solvent. Pretty basic, right? So you can have, let's say, salt or sugar water that's got a lot of sugar in there. If you've ever been to the South and had sweet tea, you probably know what I'm talking about. And you can have things with really low concentration where it's maybe part per trillion level. So concentration matters a lot for solutions. And usually chemists measure concentration using this funny term called molarity. Molarity is pretty handy, and it's a quantitative definition. And it's used primarily in chemistry and biology sometimes, although biologists will sometimes use other forms of concentration measurements. And let's define what molarity is. The symbol that's used for it is going to be a capital M, not a lowercase m, so you have to be aware of that. And it's going to be described as moles of solute divided by liters of solution. So this is the overall definition that's used. If you notice, it's not mass of solute. That's one thing students often forget is they think it's mass of solute over liters of solution. You have to convert that mass to moles in order to find molarity.
Is that a capitalized M?
Yeah, that's my terrible penmanship. This should be a capitalized M right there. Thank you. All right, so let's do some practice here. And this should help you with the last part of the pod as well. So what is the molarity of a solution when 2.33 moles of sodium chloride are dissolved to make a solution? Specifically, the solution is going to be 3.77 liters. So I'll give you a minute to try to work this out and then check with your neighbor and see if you agree. I'm going to get us started with the equation down here. Molarity equals moles of sodium chloride divided by liters of solution. So with this one, we're in pretty good shape because sodium chloride is already given to you in moles. So all we need to do is plug in the moles of sodium chloride, which we know is 2.33 moles of sodium chloride. That was given in the problem. And then we're making 3.77 liters of solution. Oops. And what answer are you getting? 0.618? Oh, let me clean this up. 0.618. And then our units would be molar, capital M.
Is that all the work you want to show?
Yep, that's really all you need to do for these. Oftentimes students get flustered and frustrated, and then they realize this is a lot easier than I thought it would be.
Can you just do 2.33 moles NaCl over, or do you need to put molarity equals moles NaCl over liters?
You don't have to, that's a good question. You don't have to include this part. I just included it there so we knew the definition and where to plug things in, whether or not the mole should go on the top or the bottom. Let's try a more challenging one. This one's going to require some unit conversions. So this one, I want you to calculate the molarity when 7.66 grams of calcium chloride, which is CaCl2, are dissolved to make 345 milliliters of solution. I guess that's not really a question, it's more of a statement. So I'll give you some time to work on that. But you're going to have to do some unit conversions for this one. So check with a neighbor and make sure you're doing your unit conversions correctly. All right, let's try to do this as a class. I heard a big yawn. I think we're ready to go. All right, first thing I would do is try to find the moles of calcium chloride. We don't know the moles right off the bat, but we do know that we have 7.66 grams of calcium chloride. So we need to convert grams away. So I'm going to put grams on the bottom. And we need moles of calcium chloride on top. I'm going to slide this over. Now the question is, which number goes on the top and which number goes on the bottom? Does anybody remember how to do this? So we know 1 mole is probably going to go on the top. How do we figure out how many grams there are in 1 mole?
By adding your
Yeah, by adding up the mass of the individual atoms. So for example, I would say, all right, the molecular weight of CaCl2 is equal to 1 calcium atom, which is 40.078. Some periodic tables might not have all those digits. Oops. And then we've got 2 chlorines. So each chlorine is about 35.453. is giving me a mass of 110.984 grams per mole. So what we can do is now take this value, plug it in up here, say, all right, this is 110.984, and when we do this, I'm getting an answer of 0.0690 moles. Is that what everybody else got?
Yes.
Okay. Of CaCl2. So we've got this first half done, not too bad. Now we've got to do the volume. And in this case, we know we've got 345 milliliters. We don't want our volume to be in milliliters, we want it to be in liters. So I'm going to put milliliters on the bottom, liters on the top. Now the question is which number goes where? This is going way back to beginning of the term.
One goes on top.
One goes on top because it's the bigger unit. So the smaller unit, which is milli, should have the bigger number. What number goes in the bottom? 1,000, exactly. Okay, so if we go ahead and do this, we get 0.345 liters. And finally, all we need to do is say 0.0690 moles divided by 0.345 liters gives us a final answer of 0.200 molar. Oops. And if you notice too, I tried to be very careful with my sig figs, so I kept the appropriate number of sig figs throughout my calculations, and you should do that for these as well.
You said M is just molar?
Yeah, capital M is shorthand for molar. That's another reason too. I see students sometimes try to take shortcuts when they're doing unit conversions, and they say, oh, I'm just going to write M for mole. And then it's like, well, do you mean mole, molarity? There's also molality, which we're not even going to get into. There's a bunch of them that all start with M's. It's really confusing, so it's always better to be overly descriptive. Okay, so let's do a few practice problems. A lot of these are similar to what you might see on an exam. So I'll give you a few minutes on each of these and see if you agree with your neighbor.
Are we down?
All right, so let's check. Raise your hand if you think it's A that's not bounced. A looks bounced to B. What about B? Yeah, B does not look balanced, right? If we look at the left-hand side, we've got 2 nitrogens, right-hand side, 2 nitrogens. The nitrogens are fine, but let's look at the oxygens. On the left-hand side, we've got 2. On the right-hand side, we only have 1. So we need to fix that. And a good way of fixing this would be to do what? I would multiply this side by 2, so I'd say 2 N2O. Now I've got 4 nitrogens, which means I would want to double my N2. And then to account for the 2 oxygens, I would just leave the O2 alone. And then this equation would be properly balanced. So being able to quickly identify and work through those can be helpful. Make sense? Okay, let's do a few more. This one's a little tricky too, and I did want to review it. So it says, how many carbon atoms are there in this entire molecule? Who thinks they got this one? This one's a little quicker. All right, so let's work through this, right? We've got, 1 carbon here. And then over here we've got 3 carbons, right? But we have to pay attention to this 2 here, right? That's basically saying everything in the parentheses is being multiplied by 2. So really this is 3 times 2, which gives you a total of 6. So 6 plus 1 would give you a net of 7 carbons. So if you do see a number outside of a bracket or parentheses, that means multiply everything in front of it by that number. Make sense?
Are these 2 questions on your test?
These were pulled from the Pearson study guide. Yep.
The 2 outside the parentheses is subscript. That means the parentheses is multiplied by 2.
Yeah, everything inside the parentheses multiply it by 2.
And not what comes after it.
Yeah, not what comes after it. That's a good question. And then the other thing, just to make it life complicated, is if you see a normal size number before a molecule, that means everything in that molecule is multiplied by 2. It's basically saying you have 2 moles of it reacting. But you don't use that for molecular weights. So it is somewhat confusing. All right. See if this one will show up. There we go. What is the mass in grams of 2.5 moles of ammonia and H3? So this would be a good one to put on an exam. So I'll get you started if you are struggling. Let's say we have 2.5 moles of ammonia. We don't want moles of ammonia, so I'll put moles down here. We want our answer in grams, so I'm going to put grams of ammonia on top. Now the question is, which number goes where? We need to find out how many grams of ammonia there are in every mole of ammonia, so I'm going to put 1 mole on the bottom. How do we find out how many grams there are? Yeah, the molecular weight, exactly. So we've got 1 nitrogen, which is 14.01, plus 3 hydrogens, which is 1.01 approximately. Did anybody find the full mass of this?
17.041.
17.034? It's going to be roughly this. We'll go with that. All right, so I'll plug in 17.03. I don't have my calculator on me, so I'm trusting you. So 2.5 times 17.03 gives you what? It gives you B? That's what your calculator says? It says answer is B. All right, so make sure you can go through these relatively quickly. Like I said, printing off those pods and going through them again, or even the practice worksheets, helps a lot. So just try to go through them. All right, a couple more. Consider the combustion of propane as represented in this chemical equation. When 7.5 moles of O2 are consumed, how many moles of CO2 are formed? Okay, so let's try this. It says we have 7.5 moles of O2 that were consumed. So I always start out with what I know. Want to get rid of moles of O2. And it's asking for moles of CO2, so I'm going to put that on top. So it looks like we have a mole-to-mole ratio we need to consider. So that's when you look at your balanced chemical equation. So for example, we've got 3 moles of CO2 up here in the balanced equation, so I plug in a 3 here. And then over here, I've got 5 moles of O2 on the other side, so I go back down here and say 5. Oops. So it'd be 7.5 moles times 3/5. And what does that get you? 4.5. Oftentimes, students with these problems think that you need to go to the periodic table and find masses and things like that. You don't need to do that with mole-to-mole conversion. Make sense? All right, one last one. A solution prepared by dissolving 0.5 moles of solute in 250 milliliters of solution would have what molarity? Would it be as simple as dividing 0.50 by 250? Not quite.
You have to convert it to
Yeah, you have to convert this to liters, exactly. We don't have the volume in liters, so I'm going to put milliliters on the bottom, liters on top, and now the question is which number goes where? 1 on the top and 1,000 on the bottom, which gives you 0.250 liters. So now we can say it's 0.50 moles divided by 0.250 liters. And what does that give you? 2.0 molar, which is E in this one. Does that make sense?